In Chapter 7, we're going to be factoring. Section 7.1 deals with factors and the greatest common factor. So first of all, it's important to know what a factor is. For these warm-up questions, it says, tell whether the second number is a factor of the first number. So basically what it's asking is, can I take the number 6, multiply it by another number, and get 50? Another way to look at it is, can I do 50 divided by 6 and get a whole number? Well, the answer here is no. 6 is not a factor of 50. Looking at number 2, is 7 a factor of 105? Can I multiply 7 times some number and get 105? Well, we can check by doing 105 divided by 7, and yes, that works, because 7 times, let's see, 15 equals 105. Number 3 is asking us to list the factors of 28. So a lot of times I'll start by writing them as factor pairs. So 1 times 28 equals 28. 2 times 14 equals 28. 3 doesn't go into 28. 4 times 7 equals 28. So those are all my factor pairs of 28, but then if we're going to list them out as factors, we like to list them in numerical order. So 1, 2, 4, 7, 14, and 28 would be those factors. More vocabulary here. Tell whether each number is prime or composite. If the number is composite, write it as the product of two numbers. So if a number is prime, its only factors are 1 and itself. If it's composite, it means there's other numbers that you can multiply together to get said number. So in number 4, the number 11 is a prime number because the only way we can achieve 11 is 1 times 11. So that means this is prime. Okay, there are no numbers that divide into that. Number 5, 98 is even, therefore is at least divisible by 2, making it composite. So 2 times what number is 98? Well, that's 2 times 49. Okay, so I thought it was important to do the warm-up here with you just for the sake of this vocabulary. So our goals for today are to be able to write the prime factorization of numbers and find the GCF of monomial terms. Important vocabulary: prime numbers are whole numbers whose only factors are 1 and itself. Okay, so there are no other numbers that divide into it. A composite number, those are whole numbers that can be divided evenly by numbers other than 1 and itself. The prime factorization of a number is a representation of a number or a polynomial as a product of only prime numbers. Let's get that a little bit. And the greatest common factor is the largest common factor of 2 or more given numbers or terms. The GCF of monomials is the product of the greatest integer and the greatest power of each variable that divide evenly into each monomial. So as we kind of talked about in the warm-up, the whole numbers that are multiplied together to find a product are called factors. Okay, so factors are the numbers that multiply together. A number is divisible by its factors, so that's why we're able to use division to check to see if a number divides into something in order to determine if it is a factor. We can use factors of a number to write the number as a product. Here's an example of the different factor pairs of 12. So 1 times 12, 2 times 6, 3 times 4. We could do 1 times 4 times 3. That's kind of redundant, adding that 1 in there, but it's okay. And 2 times 2 times 3 is taking this 2 times 6 or even this 3 times 4 and breaking it apart farther. This would be the prime factorization right here, because those are only prime numbers. The order in which we write factors doesn't change our product, but there's only one particular version that is the prime factorization that cannot be factored farther, and that's what I indicated in the previous example, also circled down here. This is called prime factorization because all of the factors are prime numbers. Technically, our prime factors can be written in any order, but technically I like to put my prime factorization in order with my numbers written in, or my factors written smallest to largest. If we're going to do prime factorization, often we use factor trees. Some people learn the ladder diagram, and if that's your method, then go ahead and use that. So let's do example 1 by finding the prime factorization of 40. Because 40 ends in a 0, I'm going to say 4 times 0 for my first branches. And by 4 times 0, I mean 4 times 10. Then 4 breaks down to 2 times 2. 2 and 2 are both prime. 10 breaks down to 2 times 5. 2 and 5 are both prime. So our prime factorizations here for number 40 would be 2 times 2 times 2 times 5. Or if we want to get fancy, we could write that as 2 to the third times 5. If we look at number 2, 33, 33 is divisible by 3, and 3 times 11 gives us 33. Both 3 and 11 are prime, therefore our prime factorization is done. So it's just 3 times 11. You do numbers 3 and 4. 192, you might need a calculator. Okay, make sure you break it down all the way as far as you can go until you only have those small, teeny tiny prime numbers whose only factors are 1 and itself. So when we branch the number 49 here, we have 7 times 7. 7 and 7 are both prime. So that's our prime factorization, 7 times 7 or 7 squared. Prime factorization of 192, a lot of us just like to continue to divide out 2's as long as we have even numbers. So we end up having 5 2's multiplying in addition to a 3. So 2 times 2 times 2 times 2 times 2 times 3, or 2 to the 5th times 3. My recommendation is A, make sure that all of the numbers that you're writing for your prime factorization are in fact prime and do not break down any farther. And take your prime factorization and type it into your calculator to verify that upon multiplying everything out, you do get the number that you started with. So now that we've refreshed our memory on how to find the prime factorization of a number, we're now going to work on finding the greatest common factor. So factors that are shared by 2 or more whole numbers are called common factors. The greatest, the largest of those common factors is the greatest common factor, or GCF. So we can go about this in a couple different ways, but one way is a little more systematic and reliable than the other. So here's an example where we have the factors of 12 listed out. Factors of 32 are all listed out. The numbers, factors in red, are those that are common, that are shared. The largest of those shared or common factors is 4. So the GCF of 12 and 32 is 4. So our two methods here for finding the GCF of a pair of numbers is to first either list the factors, as was done in this model, or second, to use prime factorization. Now, method 1 is great. However, depending on the numbers that we're dealing with, it's very, very easy to miss some factor pairs. So I tend to lean towards method number 2. So example 5, we're finding the GCF of each pair of numbers using our 2 different methods. So the first one, we're listing our factors. So with our number 32, and I think about those factor pairs again, I'm going to kind of just list them here. 1 times 32, 2 times 16, 3 doesn't work, 4 times 8, 5 doesn't work, 6 doesn't work, 7 doesn't work. Then we're back to 8, and 8 times 4. So my factors of 32, listed in order, which is important, would be 1, 2, 4, 8, 16, and 32. My factors of 48 as factor pairs, 1 times 48, 2 times 24, 3 times 16, 4 times 12, 5 doesn't work, 6 times 8, 7 doesn't work, 8 does, but then we're back to 8 times 6, and we'll kind of be in the reverse. So listing all of these in order, smallest to largest, we've got 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48. Now, there's a decent number of factors here that we could very, very easily miss one. So it's not really my favorite method, but we'll do it for now. So we want to know now the greatest of the common factors. So we have some common factors here. 1, 2, 4, 8, 16, and because 16 is the biggest, our GCF here will be 16. Now let's talk prime factorization method. So if I want to find the GCF of 45 and 60, let's do our factor trees for each. So 45, it ends in a 5, so it's divisible by 5. So 5 times 9. 5 is prime. 9 breaks down to 3 times 3, both of which are prime. For 60, 60 ends in a 0, so it's divisible by 10. So 6 times 10. 6 breaks down to 2 times 3, both of which are prime. And 10 breaks down to 2 times 5, both of which are prime. So I'm going to fully list out my prime factorization of 45, 3 times 3 times 5. And then 60 is 2 times 2 times 3 times 5. Now with this method we need to determine what they have in common. So I typically will circle. So they have a 3 in common and they have a 5 in common. So our GCF needs to be 3 times 5, which is 15. So I always say we take 1 for each pair. So I'm not going to put 2 3s. They share a 3. They each have a 3. So 1 for every pair. So 3 times 5 is 15. Is the greatest common factor. Now, if we include variables, we're going to do the same exact thing. And you can either list everything out, or you can say, okay, well, in terms of the common variable, it's going to be the lower of the powers that they both share. Okay, so in number 7, I'm going to continue with my prime factorization method, okay, to make sure we don't miss anything. So if I fully list out the prime factorization of 15x to the third, 15 breaks down to 3 times 5, and that's it. They're both prime. So this is 3 times 5 times 3 x's multiplying along. For my prime factorization of 9x squared, well, 9 breaks down to 3 times 3. Both are prime, so that's going to be 3 times 3, and x squared means we have 2 x's multiplying. So let's circle everything they share. They share a 3, they share an x, and they share another x. So the GCF here will be 3 times x, which is 3x squared. Okay, 1 for every pair. And number 8, prime factorization of 8, 2 times 4, 2 is prime, 4 is 2 times 2. So 8x squared, fully expanded, is 2 times 2 times 2 times x times x. 7 is prime, so there's no factor trees, it's just 7 times y times y times y. Now what do they share? Well, nothing by the looks of it, but technically speaking, 1 is a factor of everything. So our GCF here, if there's nothing in common, is a 1. This is considered relatively prime. Okay, so while 8 in particular is not prime itself, 8 and 7 are prime with respect to each other in that they have nothing in common. Okay, so their GCF is just 1. Okay, so here it's noted if two terms contain the same variable raised to different powers, the GCF will contain that variable raised to the lower of the powers. So if you refer back to number 7, we've got the x cubed and x squared. The smaller of those two powers is the x squared. So the GCF is 3 for the number piece, but x squared for the variable. Okay, let's take a look at number 9. Prime factorization of 18. We've got 2 times 9. 2 is prime. 9 is 3 times 3. And then that's done. So we've got 2 times 3 times 3. And then there's 2 g's multiplying. 27 is 3 times 9. And 9 is 3 times 3. So 27's prime factorization is 3 times 3 times 3, and then we've got 3 g's multiplying. Okay, so what do they share? We've got 1 pair of 3's, got another pair of 3's, got a pair of g's, and another pair of g's. So we've got 3 times g, which is 9g squared for our GCF. Number 10, looking at 16a to the 6th. 16 is 4 times 4, and each of those 4's breaks down to 2 times 2. Got to go fully prime factorization. Safest way to go about it. So we have 4 2's multiplying, and then we've got 6 a's. 3, 4, 5, 6. For 9b, 9 is 3 times 3, both of which are prime, so 3 times 3 times b. Well, what do they have in common? Absolutely nothing. So their GCF is 1, so they're relatively prime. You do number 11. Determine what their GCF is. And for the third time in the last handful of problems, we've got another one where the GCF was 1. These two terms are relatively prime. They share nothing other than the factor of 1. All right, so we've got 2 word problems here, I believe, to wrap things up. Number 12 says a cafeteria has 18 chocolate milk cartons and 24 regular milk cartons. The cook wants to arrange the cartons with the same number of cartons in each row. Why this is not working the way I want it to. Chocolate and regular milk will not be in the same row. How many rows will there be if the cook puts the greatest possible number of cartons in each row? Okay, so the hint is telling you that the 18 and 24 milk cartons must be divided into groups of equal size. Okay, therefore the number of cartons in each row must be a common factor, therefore the greatest common factor of 18 and 24. So let's start off by doing our factor tree for 18. So that's going to be 2 times 9. 9 breaks to 3 times 3. So I'll go over here and list it out as 2 times 3 times 3. 24, the factor tree. Let's go 4 times 6. And 4 is 2 times 2. 6 is 2 times 3. So 24's prime factorization is 2 times 2 times 2 times 3. So what do they have in common? They've got a 2, and they've got a pair of 3's. So our GCF here is 2 times 3, which is 6. Now here's the thing, what is it asking? It's asking how many rows will there be? So if the GCF is 6, it means each row will have 6 milk cartons. Now if we're talking about the chocolate milk, 18 chocolate milk cartons divided by 6 in a row gives us 3 rows of chocolate. In terms of the regular milk, there's 24 cartons of that, and if we divide it by 6 for our GCF, 6 in each row, that means there's going to be 4 rows of regular. Therefore, adding the 2 totals together of 3 rows and 4 rows, that's going to give us 7 total rows. Okay, so this one's a little tricky. We need to make sure we answer the question. Okay, it's going to be 6 milk cartons in each row, but that then equates to 7 total rows, 3 of chocolate and 4 of regular. And let's wrap up with number 13. Adrienne is shopping for a CD storage unit. She has 36 CDs by pop music artists and 48 CDs by country music artists. She wants to put the same number of CDs on each shelf without putting pop music and country music CDs on the same shelf. If she puts the greatest possible number of CDs on each shelf, how many shelves does her storage unit need? So again, I need to determine, we can't mix and match, I need to determine what is the GCF of these two numbers. Sometimes you might be able to know that by looking at the numbers, and hopefully you get it correct, but we're going to go through our process. So the GCF with 36 and 48, let's start off with our factor trees. 36 is 6 times 6, and 6 breaks down to 2 times 3. And another 2 times 3. So 36 is 2 times 2 times 3 times 3. I've got 48. 48 is 6 times 8. 6 is 2 times 3. 8 is 2 times 4. And 4 is 2 times 2. 48. Let's see, we've got 4 2's multiplying, and a 3. So what do they share? A 2, a 2, and a 3. So 2 times 2 times 3 gives us 12. So it means there's 12 CDs on each shelf without having to mix and match. Well, let's determine how many shelves it's going to need. So if there's 12, in terms of, let's see, the pop music is 36. So 36 divided by 12 on each shelf gives us 3 shelves of pop. And then for our country, if we've got 48 country CDs with 12 on each row, that gives us 4 shelves of country, which gives us a total of 7 shelves needed. Okay, so again, make sure you answer the question that is being asked. Now, should she probably buy a shelf or a storage unit with more than 7 shelves? Yeah, because she's probably going to get some more CDs. Those CDs are non-existent anymore, but you never know.